dark energy mysteries, how mapping galaxies is shaping our view of dark matter. Valeria Pettorino, European Space Agency.
On November the 9th, 1989, I was 10 years old. I had just started middle school, and I'd just discovered science fiction novels by Jack Vance and Philip Jose Farmer.
Thank you, everyone. I am here to talk about Euclid, a space mission by the European Space Agency, ESA, which is designed to address some of the fundamental questions of the universe we live in. What is the universe made of? Matter, normal matter, the ones we see that forms atoms, human beings, and stars, only accounts, surprisingly, for 5% of the total energy budget of the universe. The rest is in the form of dark matter and dark energy. Dark matter is still matter in the sense that it feels gravity. We don't see it directly, but it's sort of the glue that allows galaxies to form. Dark energy is 70% of the universe. It's even more mysterious. And it drives the accelerated expansion of the universe. That means that the universe is expanding faster and faster, as if there was something else, some new source of energy that contrasts gravity. We don't know what's the nature of dark energy, what's the nature of dark matter, and that's what Euclid is going to address. There are several options. It could be a particle, it could be several particles. It could be a new force that modifies gravity, like it's described by Einstein in its theory of general relativity. It could change fundamental physics. And in order to narrow down these options, we need to be able to observe very tiny effects in how matter is distributed in space and time. And how is matter distributed? If we look at very large scales, matter does not fill the space everywhere in the same way. It actually forms a network, what is called the cosmic web, where there are filaments, luminous filaments that you see there, where galaxies and clusters form. And then there's empty spaces, dark voids in between filaments. And the exact configuration of this cosmic web, how many filaments there are, how many clusters, how large are these voids, how fast they grow, this depends on the nature of dark energy and the nature of dark matter. Now, this one is a simulation that was realized specifically for Euclid. But Euclid will measure this. It will measure the cosmic web and how it's formed in space and across time in the last 10 billion years. This is called galaxy clustering, how galaxies form in space and time. But that's not it. Euclid will also measure the distortion of light. If we look at the galaxy, which is far away, and there's dark matter in between, the light that comes from the galaxy will not travel to us on a straight line, but it will be deflected. And this means that the image, the shape of the galaxy that we are observing will be deformed. The dark matter in between will act as a lens, as a magnifying glass. That's why we call this gravitational lensing. Now, by measuring this tiny deformation in the shape of the galaxy, we can reconstruct the properties of the dark matter, which is in between. Sometimes this is a very large effect, like we see on the left, strong lensing. We can see very evident arcs, even rings. But most of the times, these are very tiny effects that are not measured on one single galaxy, but on many, many galaxies. That's why Euclid will observe billions of images of galaxies. So galaxy clustering, gravitational lensing, these are hard to measure, and even harder if you are on ground. This is a patch of the sky as seen from ground. And here we cannot see the shape of the galaxies with the resolution we need. But if we look at the same patch from space with Euclid, then suddenly the resolution is much better. We're not disturbed by the Earth, by the atmosphere around Earth. and we see immediately many more sources which appear. Now, this is possible thanks to two instruments, the finest optics which has been sent up to space. Euclid has two instruments, one which measures shapes, images of galaxies. This is with an incredible camera, a mosaic of 600 megapixels. Imagine that the typical phone that you have has a camera of 12 megapixels. The second instrument measures spectra, and from there we derive distances to these galaxies. So every day we are right now receiving more than 100 gigabytes of data from Euclid. This is several petabytes in a few years. So this is a challenge by itself to store this data, process this data, extract information, and then share it with the whole community. And yet, this is happening.
3, 2, 1. Propulsion is nominal. Vehicle is pitching downrange.
It was the 1st of July, 2023, when Euclid was launched successfully to space. Quite a moment. Imagine that I had joined myself this collaboration 16 years before that moment, always working on simulated data. And now, finally, we are in a very special time in which we are receiving and processing real data from Euclid. It took a month to send Euclid to space at about 1.5 million kilometers from Earth on its final orbit. It is protected by a solar shield that protects it from the light of the sun and allows it to be in thermal stability where the instruments are cooled down and it can look safely to deep space. And on board, there is also a sensor, a fine guidance sensor, which is meant to keep the camera stable while you're taking your picture, like we did before, except that this has to happen for 10 minutes in which the camera is stable. And when it was switched on, it was actually not really working. It was actually moving all around and drawing some very artistic patterns in the sky that may be very nice artistically, but not so good for science. And yet it was up there, and so it was a lot of work from Earth, from ESA, from industry, from scientists to develop a software update that would be sent there to space and solve the issue. And this was solved together with other issues, until on the 14th of February 2024, this year, finally the wide survey of Euclid could start. Euclid will realize the largest map of the universe ever measured. It will measure all the part which is highlighted at the top, at the bottom, and in that sort of island at the bottom left. This is the Euclid wide survey. And Euclid is fast in doing this. It has a wide field of view and yet can have very high resolution. So it will cover that area, all the sky which is beyond our galactic plane, within 6 years. Also, it will measure those orange patches which are there. These are the Euclid deep fields. So parts where Euclid will pass over and over several times to reach an even higher resolution and see even fainter objects. That's why Euclid can see very rare things, thanks to its great statistics, and see new things that we have never seen before. This is only possible with a very large collaboration led by ESA that puts together expertise of many different fields, from industry to a network of universities across the world, for a total of more than 3,500 people who are working on this. And thanks to these people, we released the first data last May, which are part of the early release observations. You can have a look at that, at the link that I showed in the previous slide. These are just 24 hours of observations, and yet they show how incredible Euclid is. This comes with 10 images that were released. This is one of those images, and only in this picture, there are more than 300,000 sources, including new stars which are born in that region, which is very bright. This comes with 10 pictures, and if I look at all the pictures, it's really, I mean, it's stunning how they're all different, and it's all very dynamic. We see galaxies of different shapes, some interacting, merging, new stars which are forming. We see deep space, but we also see down to the resolution of planets of a few times the mass of Jupiter, all with the same instrument. If you go to that link, Sky, ESA Sky, you can zoom in these images and still see very, very tiny details. And finally, 3 weeks ago, we released the first views from the Euclid-wide survey. This is an image of 208 gigapixel. We would need many, many more of these screens to see it in full resolution. This is a collection, a mosaic of 260 observations that were obtained over 2 weeks. And it only represents 1% of the total survey that would be done by Euclid, of the whole map that will be realized. So right now we'll see a video where we will zoom in into this image and zoom in down to 600 times the size of the original mosaic. Just to tell you that within this image, there are already more than 100 million sources among stars and galaxies well beyond our Milky Way. I hope that this will show you how vast the universe is, and yet how incredible it is that we as human beings can actually manage to look at this, and how incredible things human beings can do when they collaborate together. So enjoy the video. We start from the Milky Way and the dust as seen by previous ESA mission Planck. The orange part is the part observed by Euclid, and we will zoom in onto one patch, 1% of the sky. May the force be with you. We're going to zoom in, and here's a galaxy cluster, which is at 670 million light years away from us. We're reaching 600 times the original size of the mosaic, and we still see a spiral galaxy in so much detail. Thank you. Thank you.